Okay, I'll start the lectures. So there will be 12 lectures in all, and we'll deal with all of the phase transformations that happen from austenite, and we'll also use the theory that we develop to design new kinds of steels, to see how very simple theory can be used to design new kinds of steels. This is a summary of all the different kinds of transformations that happen from austenite. Okay, so I'm not including carbide particles here, although I will refer to them later on. And you can classify them into two essential kinds of transformations, the reconstructive transformations and displacive transformations. Reconstructive transformation means that you have to break all the atomic bonds and rearrange the pattern in which the atoms are arranged into a different pattern. Okay? So that's like when water solidifies to ice, you don't see a macroscopic change in shape, but the crystal structure of the ice is completely different from that of water. Okay? So that requires fluid flow or diffusion. Here we change the crystal structure by a physical deformation. So this process does not require any diffusion, and all of these transformations can happen at temperatures where iron atoms cannot move within the time scale of the experiment. Okay? So I will deal with all of these transformations, and we want to deal with them in such a way that we can do some calculations and design steels. So I will give specific examples of the design of steels and the behavior of steels as a function of these microstructures. And I'm going to begin with what is possibly the simplest of all transformations, which is martensite. Okay? Martensite is right down over here. It's a very simple transformation because there's absolutely no diffusion even of carbon atoms. And some people will say that martensite is not a nucleation and growth phenomenon because plates form very, very rapidly. But the fact that you can identify a martensite plate coexisting with austenite means that there must be nucleation. Okay? So it's the same as any other transformation in steel, a nucleation and growth event. So I'm going to begin by asking you some questions, all right? So tell me what you understand by martensite. And don't worry about getting things wrong. Just answer. Give me some characteristics of martensite. Yeah, you have to participate in these lectures. So you are smiling, so tell me what one characteristic of martensite. Okay, let's make a note of that. So martensite is brittle. So remember, this is like a brainstorming session where if you get the answer wrong, don't worry about it. Okay? You must know much more about martensite than it being brittle, right? So give me some more characteristics of martensite. Hard. What else? So these are physical properties of martensite. What else do you know about martensite? Yeah. Diffusionless. What else? Yeah, so there is a clear crystallography, isn't there? Because if you look at the structure here, the plates are not forming on random planes. They're forming on particular planes and with particular orientation relationship with respect to the austenite. So there's a strong crystallographic element to martensite. There are some crucial details missing. Yeah, you know, you can buy spectacles which you can bend, right? And then you warm it up, it'll go back to its original shape. What is that? Yeah, shape, that is a shape memory effect. but the transformation produces a deformation. Just like when you do a tensile test and you get deformation, here the change in crystal structure produces a deformation. So there is a shape change. What about transformation temperature? Anything about that? Very low. Athermal, yeah. So what does athermal mean? You're right. What does it mean?
It depends on the temperature that depends on.
Excellent. So it's an athermal transformation. That means that in order to get martensite, I have to cool to a certain temperature, and I'll get a certain fraction of transformation. To get more transformation, I need to cool further. If I hold it at a particular temperature for a long time, you will not get more martensite. Okay? What else? So if I gave you a piece of steel and I said, okay, produce martensite, what would you do? Quenching, so that indicates what? We need rapid cooling. And we can think about many other characteristics. I will show you now that almost all of these are not correct. Okay? So I'm going to now go through the characteristics of martensite and demonstrate to you that almost all of these are not actually correct, even though we have it ingrained in our brain that martensite is brittle and that it's hard and that it's athermal and it requires rapid cooling. So let's go through the characteristics of martensite now. So this is what we were doing. We were trying to discover what we think about martensite from everything we've studied so far and what are its characteristics. Well, the first thing to note is that martensite need not be hard. Okay? So here are martensitic transformations in a whole variety of materials. These are steels. This is a ceramic. It's zirconium oxide. This is a solid solution of argon and nitrogen. And this is copper aluminium. You can see that martensite is not hard. So why is martensite hard in some steels? For example, here we have a Vickers hardness of 600, but not here. Why is it the case that in some steels martensite is hard and in others it is not? Yeah? So carbon causes hardening. And does anybody know why carbon causes hardening? Why does carbon cause martensite to be hard? Take it? Lattice expansion. Okay, so why does carbon not harden austenite so much?
In austenite there is some more space for carbon.
Okay. Actually, there isn't more space. If you calculate the size of an interstice in austenite, it's not that much different from ferrite. The reason is very, very interesting. If I draw a unit cell of ferrite, so these are my iron atoms, and we have a body centering atom in the middle, right? That's the crystal structure of ferrite. And carbon sits over here. It's an octahedral site. And this distance here is the lattice parameter divided by 2, right? This distance here is root 2a over 2. It's half the face diagonal. So the hole over there is an octahedron, but it's not a regular octahedron. The strain in this direction is much larger than the strain this way or that way. So it's a tetragonal distortion. Tetragonal distortion. If you look at austenite, so this is at the center of this face here. Okay. And our carbon atom is located here. This distance is a upon 2. And this distance is also a upon 2. So it's a regular octahedron. Carbon atom causes a uniform expansion. Okay? So it's like a hydrostatic strain. Strain and uniform expansion. Now, if you have a hydrostatic strain, that cannot interact with a shear stress, right? You know, when we do the pressing of powders, yeah, we put the powder into a mold and then we pressurize that. And then the powder becomes sintered, but the shape remains the same because there are no shear stresses associated with pressure. Okay? Dislocations are about shear. So a dislocation strain field has a very weak interaction with a uniform strain field. And that's why carbon in austenite causes very little hardening, just like nickel in austenite causes very little hardening because it causes a uniform expansion. Here, a tetragonal strain field has a very strong interaction with the shear strain fields of dislocations. Yeah, because after all, a dislocation is about shear, it's not about volume change, right? So, strong interaction with dislocations. With dislocations. Is everyone happy about that? Yeah, so the basic reason why carbon causes hardening of martensite in steels is because of this tetragonal distortion. If we add the same amount of carbon in austenite, there is almost negligible hardening by comparison. So carbon is like a substitutional solute in austenite. It's causing a uniform expansion. Okay? So carbon does not always cause hardening. If we had 0 carbon concentration and we produce martensite in pure iron by cooling rapidly, that would be soft. We do not need carbon to produce martensite. Martensite is simply a change in crystal structure. So if we take pure iron and we cool it rapidly, you will get martensite. Now the other thing to note, which we haven't listed over here, is normally we think of martensitic transformations happening at a low temperature. Okay? But look, here we have martensite in zirconia, which is forming at 1200 Kelvin. On the other hand, this martensite forms at less than 4 Kelvin. So the point about this temperature is not that martensite always forms at a low temperature, but it can form at a low temperature. Okay? That means that it cannot have diffusion during the transformation. It need not form at a low temperature, but it can form at a low temperature. Okay? So martensite can form at a low temperature. Form at a low temperature, but need not do so. If I asked you about the speed at which martensite forms, could you give me an idea in meters per second? Say the growth rate of martensite? Have you heard about acoustic emissions So if you go to my website, you can hear martensitic transformation happening. There's a file which you can use as a ringtone on your telephone, yeah, which is the sound of martensite. Now, acoustic emissions happen when you get sudden events. And martensitic transformation sometimes happens very rapidly at the speed of sound in the metal. And the speed of sound in the metal is roughly how much? Thousands of meters per second. Okay? Compare that with the fastest ever solidification rate, which is about 80 meters per second. Okay? So because solidification involves diffusion, whereas a deformation which changes the crystal structure can happen extremely rapidly. So martensite can form extremely rapidly. Approximately 5,000 meters per second. But it can also grow slowly. For example, in the shape memory scenario, where you're growing and ungrowing the martensite at a slow rate. So it need not do so. Okay, so the major characteristic of martensitic transformations is that when you get a change in crystal structure, you get a change in the shape. Right? So if you've got a pattern of atoms which is arranged in a square, and then it transforms into martensite, then obviously there will be a change in the shape of your sample, right? So it's just like shear deformation or twinning deformation, except that we also have a change in crystal structure. Now, does anybody know what this is? This is a virus, a particular kind of virus. Okay? And think of this as the body of the virus, which contains the DNA, and these are some sort of arms. And the virus goes and attaches itself to the surface of a bacterium. And then it operates this hypodermic needle. So here you can see it's long and thin, and here it is short and fat. And by changing the shape, it injects the bacteria with its DNA. And then it can multiply. So viruses don't have sex, yeah? They don't mate. They multiply by infecting something else. This change in shape is actually martensitic transformation in a cylindrical crystal. So this is actually a cylindrical crystal, like so, yeah? Effectively two-dimensional crystal, which by martensitic transformation changes its crystal structure, and in the process goes from long thin to short fat. And this is an actual micrograph showing this virus going towards a bacteria, attaching itself, and then infecting the bacteria. So, of course, in doing so, the virus itself no longer is alive because it's lost its DNA, right? You don't have DNA, you're not alive, right? Okay? But it reproduces by infecting the bacterium. So martensite happens in life and death as well. Okay, this is a classic movie by Tsuchiyama from Japan, where you can see the shape memory origami, right? Origami is a paper artwork, but by raising the temperature, it folds into that shape. Then when you cool it again to regenerate the original set of martensite variants, it'll unfold itself. So this deformation that I've drawn on the board is a real deformation which you can physically measure, pick up, and it can, in principle, do work as well. So when it cools, it'll flatten out again. So you can find this on YouTube if we want to watch it again. Okay, so we've said we've said that it may not be hard, and if it's not hard, it may not be brittle. Yeah. So if you look at maraging steels, maraging steel has almost no carbon in it. The martensite is produced by alloying with a lot of nickel and molybdenum. And when you quench it, it's not a hard material. It's actually extremely tough. And to get the strength, you then heat treat it to precipitate intermetallic compounds. And maraging steel is used for rocket casings. So you cannot have that brittle. It's got to be really tough, right? Just imagine the stresses on the rocket motor when it's fired. So martensite need not be brittle. How do we know that it's diffusionless? If I asked you to prove to me that martensitic transformation is diffusionless, how would you prove it? So you are taught that it is diffusionless, but if you had to prove that it is diffusionless, how would you do it? Yeah, so we can measure the chemical composition and show that it's the same as that of austenite. So how would you measure the composition? Yeah. What are the methods for measuring chemical composition on a fine scale? So typically a plate is about 0.2 micrometers wide. In lattice parameter, yeah. So yes, that's a good point, because carbon has a big effect on the lattice parameter, yeah. But it's not too sensitive, yeah. What methods do you know, which we have in GIFT and in POSTEC? Go on. You can use energy dispersive X-ray analysis, yeah, which examines basically about 1 cubic micrometer of material. Carbon is difficult. Yeah, wavelength dispersive X-ray analysis. Supposing I wanted to go to atomic analysis, how would I do it? So I want to measure atom by atom. We have the technology in POSTEC. Surface. But it's good point. It's a surface analysis. Atom probe, yeah. So we have in the nanocenter a machine where you can pull out atom by atom and measure how long the atoms take to fly between 2 points, and from that determine its chemical identification. So on the finest possible scale, you can chemically analyze and show that martensite is diffusionless. We also have this information. At 4 Kelvin, there is no possibility of diffusion, even of carbon, in the time scale of the experiment. And if it's growing at this speed, there is no way that you can have diffusion of even carbon. So these are the 3 methods. The fact that it can form at very low temperatures and it can grow very rapidly indicates that it's martensitic transformation, that is diffusionless. And we have many techniques to measure the fine scale chemical composition to prove that it's diffusionless. Everyone okay so far? Okay. What is the shape of martensite? Now, I can tell you that many research papers that I read incorrectly identify the shape of martensite. So if you had a plate of sorry, I've given away the answer. Okay, it is wrong to say that martensite is needle-shaped. Yeah, because what you're doing is you're taking something that is a plate in 3 dimensions, and when you section it, yeah, you're looking at a projection. So it looks like a needle, but in 3 dimensions, it cannot be a needle. The mechanism of transformation does not allow it to be anything other than a plate, or a plate which is thinner in 1 dimension, is wider along here and shorter along here, in which case we call it a lath, like a ruler. Yeah? So it has to have a large flat shape, a flat plane, and we will discover why it has to have that later on. But in 3 dimensions, the shape of martensite is that of a plate or a lath. So this is a typical optical micrograph, and you cannot see any round sections, right? So if it was a needle, then the probability of seeing elliptical or round sections is very high. You cannot see any like this. And when you look at your own martensitic samples, you will not find round or elliptical sections. Martensite is not needle-shaped. It's wrong to call it needle-shaped. It's a plate or a lath in 3 dimensions. Now I'm giving you all of these characteristics of martensite. We need to explain why we get all these characteristics. So today's lecture, I'm just summarizing what we need to explain. And in the next lecture, we will have the theory to be able to explain everything about martensite. Okay? Right, so the shape of martensite is in the form of thin plates or laths. And the reason for this particular shape is as follows. I indicated to you that when we get a change in crystal structure by a deformation, there will be necessarily a change in the shape of the austenite which transforms into martensite. So here, for example, is a single crystal of austenite, and supposing there's nothing surrounding it, then that is the shape deformation. It is a combination of a shear on this plane, and I'll show you later on there's also a volume change. Okay, so it's not strictly speaking a shear. It's a bit more complicated than that, but we'll get into that later. So this is unconstrained. That means there's nothing to restrict the change in shape. This is a single crystal in air. But in the vast majority of cases, we are dealing with polycrystalline samples. So there might be a grain of austenite surrounded by more grains of austenite. And that really pushes against this deformation. So to minimize the strain energy, it adopts the shape of a thin plate. Okay? Now, this is what we call the habit plane of martensite, the plane on which the martensite forms. And the average here is the same as here. Okay? So crystallographic indices of the average plane here is the same as here. But here you form a thin plate because you cause a lot of strain energy by pushing against the surrounding crystals. And by forming a very thin plate, you reduce that strain energy. Again, I will explain why a thin plate leads to a reduction in strain energy later on. But a very simple explanation is as follows. So supposing this is my austenite, and I transform it to martensite, and this is the habit plane. You can see that the displacement increases as I move away from the habit plane, right? The strain is the same because the strain is displacement divided by height. But the magnitude of the displacement is increasing as I move away from the habit plane, right? So, if I restrict the shape of the martensite to be like this, then you can see that the displacement here is virtually 0. Okay? So the reason why it forms as a thin plate is to minimize the strain energy. by minimizing the displacements. At the tip of the plate, that is why it gets down to a sharp tip, yeah? The displacement is 0, right? So if you look at the optical micrograph, you can see that the plates are very narrow at the tip. Right? So we call this a lenticular shape, a lens-like shape. Okay. So a lens-like shape or lenticular. You know, the lens magnifying glass has a lens-like shape, and that's the shape of a martensite plate. Now, we've defined what the habit plane is. It is basically the interface plane between the austenite and the martensite, the major interface plane between the austenite and the martensite. So if anybody has questions, feel free to ask now. Yeah? So the habit plane is the major interface between austenite and martensite. So gamma is austenite and alpha prime is martensite. Now, when we talk about slip deformation, yeah, slip happens on a nice close-back plane in austenite, right? A 1-1-1 plane of austenite. Yeah, is everyone familiar with that? And it happens in a particular close-back direction, which is 1-0-1 direction. Yeah. So where the atoms are most densely packed, it's very easy to slip. And similarly for the slip direction. Martensite is extremely strange. Note carefully the word approximate here, okay? These habit plane indices are really strange. 295, 315, 10, 252, and even these numbers are approximate. You cannot actually express the habit plane of martensite in terms of integers, just like you cannot express the square root of 2 in terms of integers. It just goes on forever, right? 1.414141, blah, blah. So similarly, martensite forms on strange planes with irrational indices. Irrational means you cannot express the indices in terms of integers. And, you get quite dramatic changes in habit plane with the chemical composition. So we need to explain all of this, okay? The only well-behaved habit plane is epsilon martensite in stainless steel. Epsilon martensite is hexagonal close-packed, yeah? Whereas alpha prime is the body-centered cubic or body-centered tetragonal martensite. So this forms on exactly the 1-1-1 plane. Okay? It's not an irrational habit plane, it's exactly a 1-1-1 plane. So we need to explain, first of all, why does martensite form on really strange planes, okay? Not nice close-back planes where slip happens, and in some cases why it doesn't do so, why it forms exactly on the 1-1-1 plane. So I'm going to leave you in today's lecture when I finish, yeah, with a lot of confusion, and everything will fall into place in the next lecture. Hopefully. Similarly, the orientation relationship between the austenite and martensite is not a straightforward relationship. We have the close-back planes approximately parallel. So when you read in the literature that 0-1-1 is parallel to 1-1-1 of alpha, that is an approximate parallelism. They are not exactly parallel. They might be about 0.46 of a degree apart. And similarly, the close-back directions from the two crystals, the gamma and alpha, are not exactly parallel. Okay? So even the orientation relationship is irrational, and we need to explain that. So the orientation relationship is irrational. Habit plane and orientation relation irrational, except in the case of the epsilon Martin-Site transformation. Okay, so I've already said this. Yeah, when people talk about Kurdyumov-Sachs, Nishiyama-Wasserman, they don't really mean that. Yeah, they're just taking that as an approximate relationship. You can't really measure these accurately using EBSD or even straightforward electron diffraction in the transmission microscope. You've got to do something called convergent beam electron diffraction, very, very careful measurements to pick up the irrationality of the orientation. Yeah? To measure an orientation difference of 0.5 degrees, you cannot do with ordinary electron diffraction because the zone axis can be this way or that way. Yeah? You know, when you're using thin foils, you can get Bragg diffraction even when you're not at the exact Bragg orientation. And similarly, EBSD, don't believe anything which says that the accuracy is 0.5 of a degree. Yeah? If you just measure on the austenite itself, you'll see a big range in the orientation of the austenite. Okay, athermal transformation. Yeah? What do we mean by athermal transformation? You defined it very well. That look, if I'll explain this equation later on, but this is the volume fraction of Martin-Site, and this is the Martin-Site start temperature. That means the temperature at which Martin-Site first begins to form. Okay? And this is the actual temperature, which could be anywhere below ms. In this equation, which tells you the volume fraction of Martin-Site as a function of temperature, there is no time. Okay? That means that if I cool to this point, I can calculate the amount of Martin-Site, but it will remain constant on my time temperature transformation diagram, no matter how long I hold it at that temperature. Okay? So it's what we call an athermal transformation. That doesn't apply here. If I hold my austenite, I'll get 1% perlite. Hold it longer, I get 50%, 95%, and so on. Okay? So that's the difference between an athermal transformation and a transformation which depends on time. The reason why this is not strictly true is that things are happening very, very rapidly. If we could observe something that's growing at 5,000 meters per second, there would be a time dependence. Okay? Right. We need to think about the structure of the interface between austenite and Martensite because that interface has to be able to move very rapidly without diffusion. Okay, so that's the basic condition for Martensite, that the structure of the interface between gamma and alpha prime must permit rapid transformation without diffusion. Now, supposing you look at a grain boundary in a transmission electron microscope, what would you see? Yeah? You were saying something? No? Supposing I look at an interface in a transmission electron microscope, what would you see? Yes, yeah. If there is perfect match, then we would see nothing. Yeah. But in general, what would you see? What would an interface look like in a transmission electron microscope? There'll be a series of lines. Now, do you know what those lines are? Okay, not to worry. Let's create an interface, okay? So how do we create an interface? Well, we start with a single crystal. If I cut it along here and I tilt the two parts with respect to each other by an angle theta, I don't get an interface, I get a gap here. Yeah, so this is not yet an interface. I need to fill that gap with something to make the two crystals connect with each other, right? So what do? We put dislocations inside that gap. And those dislocations fill up the gap because in this case there are edge dislocations, and edge dislocations have an extra half plane, don't they? Yeah. So if you looked at the structure of an edge dislocation, it would look like this. Yeah. This side is tilted with respect to this side. That's the operation we did in the previous slide. And this half plane is just filling up the space, right? Is everyone happy with that? So if I put enough dislocations in here, then the gap disappears. Okay? So these are dislocations, and the spacing of the dislocation is d. And simple geometry tells you that the tangent of theta is equal to the Burgers vector of the dislocation divided by the spacing. So if I tilt more, then the spacing decreases. Okay? So this is the dislocation model of an interface, and that's exactly what you see when you look at the interface in a transmission electron microscope. It consists of a series of dislocations. This is a particularly simple interface where we have just tilted the two halves of the crystal. You could have a more complicated relative orientation, and in general you might have three sets of dislocations with different line vectors to define an interface. But an interface is nothing more than a set of dislocations which allow the two crystals to connect. Okay? And you can see these dislocations in a transmission electron micrograph. I'll bring along such a micrograph in the next lecture. And this is the very simple relationship between the misorientation between the two halves, the character of the dislocation in terms of the Burgers vector, and the spacing. And as you increase theta, eventually this model doesn't become meaningful because you start to get the overlap of the cores of the dislocations, right? And that's when you have a completely incoherent boundary. Everyone okay with that? Okay, now we need to think about what is the kind of interface that must exist between austenite and martensite, because it has to be a special interface which allows rapid transformation and without any diffusion. Right, so here are two kinds of interfaces, again with dislocation structures. This I have called glissile because the Burgers vector lies outside of the plane of the interface. So these dislocations can move. If you apply a stress or you cool the material, if this is martensitic transformation, these can move and cause the deformation without requiring any diffusion. Yeah? On the other hand, this is a sessile interface because for these dislocations to move, you would require climb of the dislocations. Yeah? Is everyone familiar with climb? Yeah? So here we have a dislocation lying on this particular plane. Okay? If I wanted to move onto another plane here, then I've got to lose this material. Right? I've got to lose it by diffusion. That's called the climb of a dislocation. So an interface like this cannot move without diffusion. For it to translate this way or that way, you need to add atoms or remove atoms from that extra half plane. So this is the kind of interface that must exist for martensite because it doesn't require diffusion. It's basically the glide of dislocations. They happen to be interface dislocations, but it's the glide of dislocations. So must be glissile. Glissile. Climb requires diffusion. Everyone clear? Now, again, this is a very simple structure of the interface. And I mentioned to you that in general, I might need 3 sets of dislocations to accommodate the misfit between 2 crystals. Yeah, because we only did a very simple operation where we cut a crystal and we tilted the 2 halves. But I can do many other operations to give the relative orientation, right? So in general, 1 set of dislocations is not enough to accommodate the misfit. So we have to ask the question, with martensite, can we have more than 1 set of dislocations in the interface? Okay? So if I'm looking at the plane of the interface, so we are now looking at the plane between martensite, which is behind the board, and austenite, which is ahead of the board. Should we have a structure with just 1 set of dislocations, or is it possible to also have a structure like this with more than 1 set of dislocations? Yeah? So here we are looking at the habit plane, which is the board. Behind is martensite, and in front is austenite. If we look in a transmission electron microscope, is this what we should expect with martensite or something more complicated? So let's try and answer that question. So that clock is still not working, you know. It's stuck at 3:30. Okay, so I might carry on lecturing until it moves to 4:30. So let's imagine we have 2 dislocations. Here, this one is an edge dislocation. Its Burger's vector is pointing at 90 degrees to the line vector. And this one is a screw dislocation, where the Burger's vector is parallel to the line vector. What happens when these dislocations cross? Well, exactly what happens when a dislocation moves through a crystal. You will create a step. Yeah? And on this dislocation here, the direction of the step is the Burger's vector of B1, here. And on this dislocation, the direction of the step is the displacement B2. Yeah? So when they cut each other, you create steps which correspond to the Burger's vector of the cutting dislocation. Yeah? So these are called jogs. Okay? They are defects on dislocations caused by the intersection of 2 different dislocations. Now, a screw dislocation can move on many different planes, right? Any plane which contains its Burger's vector, it can move on that plane. But once you have introduced this jog, that becomes impossible, yeah? Because this jog is no longer a screw. This jog is no longer a screw. The Burger's vector is still pointing this way, but the line vector is different. So this dislocation was glissile and becomes sessile by the cutting. Yeah? Now it will require diffusion to move. So in the interface between austenite and martensite, you cannot have more than 1 set of dislocations. Very, very important result. So in the interface between gamma and alpha prime, we cannot have more than 1 set of dislocations. dislocations. So just summarize over here. A glycol interface cannot contain more than one set of dislocations. It will be like this if you look in a transmission microscope, not like this. And martensitic transformation is only possible if you can create such an interface between two crystals. And you can only have one set of dislocations if there is no distortion along this line. Yeah? Here. Because if there is distortion along this line, you will need another set of dislocations to accommodate that. Okay? So this line we call an invariant line. Invariant line. That means that there is no distortion or rotation between the austenite and martensite along that direction. Okay? So there is no distortion or rotation along that line. No distortion or rotation along that line. The austenite and the martensite match perfectly along that line. Okay? The atomic arrangement in the austenite and the martensite match perfectly along that line. So there is perfect match along that line. If you cannot find perfect match along one line between the two crystals, it's not possible to get martensite. Okay? So if I gave you any two crystal structures, right, whether it's in ceramic or brass or whatever, and I asked you the question, is martensitic transformation possible between these two crystal structures? Say one is monoclinic and the other one is cubic. If you cannot find one line which is coherent between the two crystals, it's not possible to get martensitic transformation. So now you are able to predict for any two crystal structures whether or not martensitic transformation is possible in principle. Yeah? So it's a very important result that martensitic transformation is only possible if the deformation which changes the parent, in our case austenite, into the product, which is martensite, leaves one line undistorted and unrotated, an invariant line. If you cannot find such a line, then martensitic transformation is impossible. So the deformation which changes austenite into martensite must leave one line completely undistorted and unrotated. Is everyone clear about that? This means that you can never get a fully coherent interface between austenite and martensite because we are only leaving one line undistorted. If we leave one plane undistorted, then that's a fully coherent interface. But the minimum requirement is to find one line so that we can have just one set of dislocations in the interface. So, just in today's lecture, we are now able to define whether martensitic transformation is possible in plutonium with all its different crystal structures, or in any other system. If you can find one line which is undistorted and unrotated, it's possible in principle to get martensitic transformation. If you cannot find such a line, it's impossible. So the interface between martensite and austenite must be semi-coherent in a special way that there is just one set of dislocations. This is just repeating the same thing which I drew on the board. Okay, this is the reason why the interfacial energy between martensite and austenite is really quite small. Yeah, this is 0.2 joules per meter squared roughly, and that compares with a twin boundary which is fully coherent, and an incoherent boundary which is about 4 times that, and the surface energy of window glass here, which is about 1 joule per meter squared. The energy is low because there's quite a lot of coherency along this direction. Okay? This is an interference micrograph. It's called a Nomaski interference micrograph, and the color represents height. Okay? So the specimen was austenitic when it was polished completely flat and then allowed to transform into martensite. And this is not etched. We are looking at the deformation of the free surface caused by the formation of these martensite plates. So it's a real physical deformation, just like slip or twinning, except that we are changing the crystal structure at the same time. Okay? In slip and twinning, you don't change the crystal structure. But with martensite, you deform and you change the crystal structure. So this is one method of looking at the change in shape. And the change in shape is not actually just a shear. Supposing I take a crystal of beryllium, right? Now beryllium is a metal, but its Poisson's ratio is 0. So if I pull it, then I only get a volume change. I don't get a contraction. I get a volume change which is normal to the habit plane here. Okay? So this is just uniaxial dilatation. If I shear something, then I get a shear strain here, but I don't get any volume change. Shear does not cause a volume change, right? Shear is only changing the stacking of the planes. It's not causing a volume change. If I add these two up, that is what martensite does. You have a shear deformation and a volume change, normal to this plane. Okay? And the shear deformation is very large. It's about a quarter. Okay? Can anybody tell me typical magnitude of an elastic strain in steel? So if I apply a stress of 200 megapascals, what is the strain? Elastic strain? What's the modulus of steel? Take a guess. What's the elastic modulus of steel? The Young's modulus? Come on, somebody must know what the Young's modulus is. What is it?
200 gigapascals.
Yeah. So the Young's modulus is 200 gigapascals. And if I apply a stress of 200 megapascals, then the strain is equal to the stress over the modulus, which is 10 to the minus 3. Okay? So it's very, very small. Look at the size of this deformation. Huge. Okay? So it's a strain of 0.26 shear. And the volume change is of the order of 3%. Of course, it depends on the lattice parameters of the austenite and martensite, but typically of the order of 3%. So this is a small term compared with this, but nevertheless, there is a change in density when martensite forms in steels. So this is a uniaxial dilatation, a shear, and this is what we call an invariant plane strain. It leaves a plane undistorted and unrotated. Now you should be concerned. Yeah? I've sort of said that the minimum condition is we should have an invariant line. But when we look at the shape change, it looks as if there is a plane which is fully coherent between martensite and austenite. Yeah? You know, that interference micrograph and many other experiments that we can do shows that there is a plane which is undistorted and unrotated between austenite and martensite. So it's as if we can produce a fully coherent interface. This is just to show you that when I draw these diagrams, we are looking at a macroscopic scale. On a microscopic scale, of course, when the interface moves, it's producing a series of steps. Yeah? So on a macroscopic scale, this looks relatively smooth, but actually there's steps equal to the Burger's vector of your interface dislocations. Okay? Right, so going back to the strain energy diagram that I drew here, the reason why the martensite adopts a thin plate is to minimize the effect of these displacements. Okay? The strain is not varying along here, but the displacement is varying as we move away from the habit plane. So having a thin plate minimizes the strain energy. This is the strain energy per unit volume. This is the shear modulus of the austenite, the shear strain, and the dilatational strain, and the thickness over the length ratio. So if I make my plate thinner, then I reduce the strain energy. What is the origin of this equation? What is the strain energy per unit volume on that diagram? I'm just applying Hooke's law. Yeah, stress versus strain. What is the strain energy per unit volume? Area under the curve. So this is the strain energy per unit volume. It's equal to half sigma times epsilon. Yeah? And epsilon is equal to sigma upon the modulus. So it's equivalent to half. Actually, I want to do it the other way around. I want to write sigma equals the modulus over equals modulus times epsilon. So that's equivalent to half modulus times epsilon squared. Right? So from this, you see that the strain energy should be related to the modulus, directly related to the modulus, which is what we have here. Sorry about the terminology here. This is modulus and this is strain energy. Okay? It should be related to the square of the strain. So here is the square of the shear strain and the dilatational strain. This term here, the thickness over length, I've explained to you on this diagram, but it's too complicated to derive. Okay, so you need Eshelby's theory of elasticity to reach this simple equation. The theory itself is very long, and I'm not going to do it, but you can find it in Christian's theory of transformations in metals and alloys. But you can understand it by looking at this diagram. Okay? So this is the reason why martensite forms as thin plates. Actually, this is also the reason why mechanical twins form as thin plates, because mechanical twinning is also a shear deformation like this. Okay, so just to finish and summarize, there are some difficulties in the data that I've presented. First of all, you saw that we have very strange habit planes, right? 3, 10, 15, and even that is approximate. The orientation relationships are not rational. That means the closest packed planes are not exactly parallel, neither are the closest packed directions. The shape deformation is an invariant plane strain. That implies that there's a fully coherent interface between the austenite and martensite. And I will show you in the next lecture that's impossible. Okay? It's impossible to get a fully coherent interface between austenite and martensite. But nevertheless, when we observe the shape deformation using the interference microscopy or many other techniques, it's an invariant plane strain. It leaves a plane undistorted and unrotated. So these are the difficulties which led to a very, very major breakthrough in the theoretical metallurgy, which explains everything. everything falls into shape. You can exactly predict the crystallography of martensite, the shape of martensite, and so on. And that we will do in the next lecture.